So my name's Trent Hare. I've been at the USGS for about little longer than 30 years. I've kind of grew up using GIS for planetary, specifically for geologic mapping. And so a lot of this talk is more along the lines of how do I find data? Fortunately, you're living in a time now where a lot of the data works. There's GeoTIFFS, there's shapefiles, there's GeoPackages. And so understanding those boundaries between, say, a PDS planetary archive and a GIS is still difficult at sometimes, but it's much easier. So I'll plan to go through a quick outline for introduction into what astrogeology is. And then I'll just jump into some of the things we've been supporting over the last decade plus, including some really new things. And you'll see those come up as tiled WMS stack and capabilities in QGIS. You'll notice that I'm using the latest and greatest version, which has this change, and not all OSs have this update just as yet. But QGIS is changing for the better, and we still have some issues, but we're making progress with that as a planetary GIS application. So let me go forward. So USGS, we are part of the, we've been involved in the Apollo missions. So we've been around for more than 50 years. We have scientists and a lot of technical staff. We support the ISIS programming environment or software environment to go from a level 0 or a raw data product into a map projected surface product. For images, we support DEMs, but we've also been highlighting the need for what we call foundational data products. This is a term that's used a lot in earth science. It means foundational data product is something that you build from. So if you're making a map and the map keeps changing underneath you, that's not good. So we want to, whenever we want to make a map, we want to try to look for things that are considered foundational. And that means that they're controlled, they're based on geodetic networks, they're topographically controlled, which means that they've been orthorectified to the surface. And then there's another term we call framework, which are the data products that ride on top of the foundational products, like compositional maps, nomenclature, and geologic maps. So we're trying to get this nomenclature out into the world of, hey, I'm doing a map. Are you sure that it's been controlled? Are you sure that it's not going to change? And if it is, understanding that it's going to change. It's okay if things are going to change, but it might mean that you might have to remap again and again and again. Planetary surfaces are not well known, as even on Mars, the relative accuracy of any mapped is basically 100 meters. So the uncertainty is 100 meters, and that's including even the landing sites that we've done. The Jezero landing site map we helped create is probably the best tied localized map we've ever done, and it still has 100-meter uncertainties, if and potentially more. So part of the offerings that we support at Astrogeology is the Mercator GIS Lab, and that includes updating some Python toolboxes, some Esri add-ins. We do contract tools. For example, we helped initiate the Crater tools conversion to Python. We do support a lot of Python scripts. We've been working on YouTube tutorials, but we've just had a lot of time getting those out in the last year or so. We do a lot of technology testing, and that's essentially what I'm presenting on. For example, in 2019, we initiated a work with Esri to do very, very huge tiled web services, and we'll do a demo of that later. And then we also represent the planetary working group or planetary community at the OGC, Open Geospatial Consortium. And USGS has plenty of standards working groups also. So we're trying to make sure that we implement these within known standards. We're not trying to reinvent the wheel. We don't want to make new formats if at all possible. We want to integrate existing formats to work for planetary. So part of this whole idea of framework and foundational data products is born from this idea of spatial data infrastructure. And that essentially is kind of a whole environment to promote accessibility and interoperability of spatial data. And there's a good paper, Andrea Nass has one. One of our employees, Jay Laura, has one from 2017. But it essentially is understanding how the people and the data connect to each other through policies and standards and basically accessibility, or how the data gets from the actual satellite all the way processed to the scientist. And so understanding that workflow really helps you understand which technologies you need to focus on. So one of the things that we're trying to understand and promote in the community is this life cycle approach to geospatial data, understanding that you need well-controlled foundational data products, understanding that you need good tools that support planetary. We grew up in when I first started, there was a lot, every application we tested, we needed to make sure that the planetary support was solid. And even now we're struggling with some things in QGIS, but fortunately, as an open source package, we have some control over how that's maintained. We try to maintain long-term archives and web services such that some data is readily available at all times. Not everything, but some. And then community-driven standards. So again, helping the community understand what standards they need, but also getting feedback from the community on what we should apply. Technology keeps on advancing. We have cloud accessible data sets now. What does that mean for these type of applications? So our goal is that spatial data should just work. And often that's not the case in planetary. There's a lot of instrument teams or a lot of missions that produce tons and tons of data, but doesn't mean it's ready for mapping. And so understanding that and understanding potentially how to process the data is a benefit, but also such that we get to an kind of an evolution in our science that data should just work for the most part. Understanding that data is still important, but when you have a base map, you don't necessarily need to know everything that went into generation of that. So I'd like to promote, there's a lot of things out there for the community to help with. And this includes, we'd love to have students, we love to have professionals, scientists, technologists, data scientists to help with these working groups. One, we just had a meeting at the International Cartographic Association, and there's members working towards in situ rover symbologies right now. So that's a current ongoing task. MapSit is a NASA and ESA supported. There's anybody's welcome though, and it's supporting the idea of spatial data infrastructure and the planetary data ecosystem. The IU, of course, has several working groups, and two of the ones that we are familiar with are nomenclature and coordinate systems. So if you're interested in getting your hands dirty in geodesy and coordinate systems, there's working groups available to join. And again, it doesn't matter the age, your experience, it's just good to get anybody in the community interested. We also have support in the basically involvement in the Open Geospatial Consortium, and that's through the Planetary Domain Working Group. And the OGC supports things like QGIS and coordinate reference systems, but it also supports interesting things like GeoPackage and GeoTIFF and the well-known text planetary projection definition. So all these groups kind of add into our ecosystem, our data ecosystem. So understanding, if you have any interest in any of these, please contact me. I'll get you in hold of the chairs. The evolution of planetary GIS services, this is kind of my viewpoint. Before we hit the 2000s, we did start seeing proprietary interactive web maps, and we started using what are called GIS world files to control everything. GIS world files were the most basic method to be able to bring in raster data into GIS applications. So we quickly moved from that into into things like GeoTIFF. And fortunately, GeoTIFF was robust enough to support our planetary domain. As we move forward, in the mid 2000s, USGS started to push geologic mapping to GIS. That meant that everybody who was funded to do a GIS or to do a geologic map was required to do it in a GIS. And that's a good thing. That's the whole reason behind this class is such that you come away with this idea that if you're going to be doing mapping, geologic mapping, you're going to need to use a GIS. Illustrator without the GIS plugin is simply not enough anymore. You can see that we started to have a digital distribution for PDS for our data archives. ArcMap and Global Mapper had built-in planetary projections, and that maintains today. We just worked with Esri this last week to talk about new planetary projections in ArcMap. We started supporting planetary WMS and proposed IU codes for these web mapping services, and I'll talk more on that. The community added GDAL support for planetary formats. GDAL is a library to support ISIS and Vickr and PDS directly. It's mostly for map projected data. And actually, instrument teams started to adopt GIS type formats. We can see that HiRise and the MOLA team adopted GeoJPEG 2000. There's been some label issues in those, but we're still surviving. Hopefully when they update it to PDS4, we'll fix those. HRSC team actually supported GeoTIFF as part of their downloads. Excellent step forwards for the GIS user. During the 2010s, there was this giant kind of web map leap forward. The geoscience node, there was HRSC viewer, LunaServe, Google, and then you started seeing applications like JMARS and QuickMap and Trex and MMGIS. And that's still happening today. We had a project in Europe called Vespa, and that included they were tackling GIS issues like supporting WMS and QGIS and ETAP. GeoFits was created. And then there was planetary viewers created off of existing programs like Cesium. Community training like this started happening kind of in the mid 2010s. PDS4 now supports GIS vectors and GeoTIFF as a format. Tiled WMSs are using layers that are terabytes in size. This NASA is supporting or trying to understand how to move forward with a planetary data ecosystem. That's still very in its infancy. We don't know where that's going to head. It's not necessarily even funded yet, but it's interesting that the PDS was kind of always, and the PSA was kind of always recognized as this is your ecosystem. But I think we grew up understanding that not the PDS and the PSA, our archives, don't necessarily give us exactly what we need for analysis ready data sets. And I'll talk to that term. Now into the 2020s, we're starting to see things like STAC, very popular in the earth sciences, and we're starting to adopt those for planetary. And then I'll talk about planetary projections later. So what is a WMS? Very simply, it's just a very simple standard to allow say astrogeology or a university or any of the instrument teams to support streaming mosaics online. So it's been around since the late 90s. It does require a map server, which means that there's some server sitting at the host that's pointing at these mosaics and allows the GISs to access data from there. It's very typical of, say, Google Maps or JMARS. Everybody's using similar technologies to stream this data. In the mid 2000s, the realization that WMS was a little slow, not very optimized, the group came out with tiled services or tiled mapping services, TMS. And that actually is, they're at fixed scales. There's millions of tiny little tiles that are optimized for streaming across the web. And so you'll see that we've supported both now. I'd like to point out this presentation will be made available, but there's lots of kind of tips and blogs on how to interact with our WMSs. I'll do some demos too. So WMS, it has some staying power. It's been around for a long time, but it's so simple that it's still useful. The interfaces can still deal with these Earth-centric issues. QGIS, even though it comes in as Earth, we can override it such that it's on Mars or the Moon. ArcMap can do the same. Almost anybody who can, even the web applications, Open Layers and Leaflet, can understand how to override these issues. And why are there still Earth-centric issues after so many years? It's because of the standard, and the implications of understanding how to deal with that standard has been difficult. So one of the things that we implemented this in the last couple of years is the second version of our IU codes. And again, it might be too late, but it was still something good to strive for. So we're trying to implement planetary projection codes into these servers. And there's several instances out there. We actually had one that we retired, the USGS WMS server. ASU's LunaServe, if you want to host a server, still has the older codes in there. Jean-Christophe actually implemented a map server branch with planetary codes in there. So no matter what we do, breaking away from an Earth-centric standard is still tough. This one is specifically tough because it's so heavily tied to a Earth-coded standard. So as it still feels like, I can't believe WMS is still a valid technology. It's just so simple that it works. And so you'll see that a lot of us have moved towards tiles and streaming formats like COGS into the near future. So WMS is still around. You'll still hear about it, but it doesn't mean it's probably starting to see it sunset. So WMS layers, we probably have for about every major body in the solar system, we support a WMS layer. That means that we support streaming a base map as a layer, real time into your GIS. And again, there's some quirks to deal with, but it should work. And the reason why we support these layers is because we use them for our planetary names interface. We support it for our geologic mappers, and just for any other interface out there. And you'll notice that we're not the only server. There's plenty of servers out there that support this technology, WMS. So again, here's that posting. And now I'll switch to kind of the latest revolution of WMS. It's called tiled WMS or tiled map services. These again are made from very thousands or millions of tiny little JPEGs or PNGs that are organized in a certain way such that they're optimized for streaming. And the problem with the tiled WMS is that it actually might be seeing a sunset too. It takes a lot of time and effort to actually host these, to create them. So you just can't have a mosaic and host it and expect it to work. We actually are getting to the point where there's what's called tiled or dynamic tiled services. But these are, once you generate it, then it's very stable. You just need a website. You don't need a server. They just need to have an address, and you can have lots and lots of data. You can have many layers. One of the problems is it's usually locked to a single map projection. And again, we're somewhat regulated by what Earth has generated. And so Google made this thing called Web Mercator so popular that a lot of the engines that we're currently supporting are locked into this Web Mercator, which is horrible for planetary. It's great at the equator, but when you start getting towards the poles, Mercator just doesn't work. It actually doesn't exist at the pole. So there are, fortunately, tiled mosaics work in any map projection, and it's getting easier to break those rules of being Web Mercator, say if you want it in degrees or if you want it in a local projection. I'll actually do a demo of this later because it's very interesting to see what we did, and I'll have some slides that talk about tiled WMS. So this was a technology workflow we did a couple years ago, and it included 50,000 JPEG 2000 high-rise images, and that ended up being about 200 terabytes of data. Once we uncompressed and converted it to 10-bit, what we call MRF, is a highly optimized format for web. It's meta raster format, and we used an open source compression called Lurk. Both those format and compression, actually the MRF format was generated by Lucian Plesha at JPL before he moved and started working for Esri. The Lurk compression was open sourced by Esri, and it's a very good configurable compression. And so, but there's a lot more coming down the road. We've converted all these using a 100-node cluster. The actual mosaic, it's called a discrete mosaic, ended up being, without any compression, would have been 4.4 petabytes, a single layer, 4.4 petabytes. Because it was compressed, we were able to get it down to 2 terabytes from 200. No, actually, I'm sorry, it was 19 terabytes. So the total size, once fully compressed with pyramids and tiled into this MRF format, was 220 terabytes. And then we actually transferred that to an Amazon S3, and it actually supports a tiled and a WMS at the same time. So it is a pyramided single database. It understands tiles and it understands WMS at the same time. So it just happens to be a smart server. So anyways, there's capabilities here that we don't have to necessarily worry about size anymore. In earth science, they have petabytes upon petabytes of data. For us, it's rare to have this much data, and so we still haven't hit that cap. High rise was a good test for us, and it's simply a test. This is that MRF format. Again, it's open. It's within GDAL. We used Lucian's program called MBuilder to make this, and it basically is it's kind of like a database on a single file database, analogous to kind of like a GeoPackage almost, but it is basically an indexed raster file. So it's very good for giant mosaics, and it's very good for mosaics that actually have null tiles. So there's no data there. So anyways, enough said about that, a little bit too much in the weeds, but we don't have to worry about volume anymore. These servers can handle it. Using cloud hosting, we can handle things like 20 terabyte mosaics. So this gets into kind of the latest technology we've been looking at. And again, we're not generating this on our own. This is Stack is a new standard that has been around for probably about 3 years now, maybe a little longer. And it really was meant to address how do companies like Planet, how do companies like USGS that support Landsat, or Europe that supports Sentinel-1, Sentinel-2 data sets, how do they get people individual images, not mosaics, but how do they release individual images? So if you look at the acronym STAC, Spatial Temporal Asset Catalog, it really is about geospatial data, and critically important is time. So understanding how spatial and time fit together to release data and make data discoverable. And so Stack is a very kind of a simple idea to meet the need of petabytes and petabytes of individual images. And it's not, these data sets don't need to be processed. They are ready for analysis out the door. And that's what we mean by ARD, or analysis ready data. Some people call it science ready data. So this Stack was generated by the Planet company because of their wealth of data that they're releasing. And so let's walk down this and see how you utilize Stack, and how we're starting to utilize it, and how it works in QGIS. So here's a little animation from the stack, the planet guys. Basically, they're just basically showing you that once you find the data set, what do you do with it? There's a little previewers. There's a list of what's called assets. Assets, say if you have an image, it's not just a single image, it's also the metadata, it's also the accuracy. It could be kind of a cloud coverage. So all these, the assets behind one stack entry is critically important idea. So it's, you haven't just found one image, you found an image and a set of information for that image. And that's its term, assets. And we'll get back to that again. Stack hasn't really locked in on a format, except for they have, for now, opted to use cloud optimized GeoTIFF, or COG. And COG is just a special fancy version of GeoTIFF that allows for streaming. So the idea behind Stack is you have an individual image and it's represented and compressed in a format called COG, generally hosted on a cloud, Amazon or Google or Microsoft. And I can utilize that because it's optimized for web streaming directly from the cloud. I can download it and it's simply a GeoTIFF. Or I can drag it into my browser and it works directly from the cloud without downloading. Again, very critical that Stack is meant for that individual data catalog. So Stack is independent of format, but it's very married to COG right now. And you'll see that as COG might come out of favor, you might see different formats or different compressions. There's a lot of interest in, I forgot what it's called, but Z array or one of those array formats that might take over, or it might be embedded in COG. So it's an interesting thing to think about. We've kind of tackled the idea behind streaming mosaics. We've tackled the idea behind, we haven't really done streaming vectors very well. There's capabilities to stream vectors. That's never really caught on too well. And now we're trying to figure out, how do we stream individual images that are ready for science? These are not the raw data products. These are processed and ready for science. So we have a lot of beta sites and we have a lot of beta examples. And so you have to trust me when I say that sometimes these sites will go down. We're right in the middle of kind of solidifying these this year. So there's a link for our beta docs that talk about Stack. There's a link for our initial Stack browser, which is a community-driven browser for Stack catalogs. And then we have, actually in our docs, we have examples for how to use in QGIS. What's interesting and great to see in a open source package like QGIS, QGIS supports cloud optimized GeoTIFFs better than any other application I've seen thus far. So while ArcMap and Envy and other applications will probably have it soon, if they don't have it already, the QGIS had it very early. And so so that's one of the benefits of having a nice quick release cadence and that it's open. So QGIS has COG support for the last year or so or more. So let's take a little bit of a deep dive into cloud optimized GeoTIFFs. Very easy to make, very easy to support. All you need is a web service, cloud hosting service, and your data products can become streamable. No server, just a file, just an HTTPS address, and you have made a streamable data service. And one of the things that we've talked a lot about in the data ecosystem world is it's great to have tools like JMars. It's great to have tools like the Mars Trek and Moon Trek, but you can't have a single place host every single bit of data. There's never going to be the ideal of one-stop shop for all planetary data. So having different groups, whether it's ESA or JAXA or NASA, USGS, support interoperable streaming data sets is going to be kind of the way of the future. So understanding that yes, we can make these data streamable simply by converting them to a standard TIFF that happens to be streamable. And so the idea behind COG is that it's efficient imagery data access even from a website. There's reduced data duplication. So we're trying not to have multiple copies everywhere. So you have a data download for a GeoTIFF and then you have it tiled so it's optimized for a web browser, and then you have a version that's compressed. Then you have a version in the archive. So we're trying to reduce that duplication. Let's make it downloadable and streamable at the same time. There's actually even ways to make it dynamically tiled for free. There's programs out there using Raster.io in the GDAL library to make on-the-fly dynamic tiling services out of COGS without copying them. So we really do see a bright future in this format. And the benefit behind COG is it's just a TIFF. So you can open an 8-bit or 16-bit TIFF in Photoshop or any GIS. It's not a new format, it's just a specialized handling of a format. So I'm going to jump into the kind of the QGIS demo. I'd like to ask to make sure I'm going to stop sharing and then reshare my whole screen and make sure that it's still visible. So I'm going to do my whole screen. And hopefully it's not too small. I apologize if it is. The first thing you'll notice in QGIS is I'm running the most up-to-date 3.22.3, which you probably were, it's probably not a good idea to run. We want to actually run the long-term supported one. I think that's 3.16 right now. Number one, there's some planetary issues with the newer versions, although I think I'm starting to document how to get around those. And I'd like to point out right now, you can see that you're going to get this everywhere. There's no transformation available. I know exactly why this is happening. This is within the Proj library. It is a check they've added in the last probably 3 years or 2 years that says, hey, you're trying to project me from Earth to the moon. And that doesn't make sense. We've been using that style of workaround for years, embarrassingly enough, but they finally caught us, and now they're doing checks in the libraries to say, hey, why would you ever do that? Why would you go from Mars to moon in a single transformation? So a lot of this has to do with that. A lot of it can be ignored. It is doing the right thing behind the scenes. There's some weird things about geodesic style measurements, which means measurements on the sphere, which are still hampering. Hopefully we'll fix those bugs. But initially, you'll notice that I'm going to do some workarounds here. They're somewhat still embarrassing. We've been working on these for years, but they do work, and they are accurate. They will make for accurate measures, and they will make for accurate science. So, while you have these issues, make sure you look at them so you know exactly what's happening. But in general, you can essentially dismiss them. And so I'd like to show that for the GDAL QGIS version, I'm using 3.4.1. At probably around 3.0, we introduced PDS4. So you'll start to see more PDS4 support in QGIS. And then in Proj 8.1 potentially, or 8.2, we introduced a bunch of planetary projections into Proj. These are these coded projections that work well for streaming services. As much as I hate these codes, I still see the need for them. Ideally, we want to use very verbose map projection definitions, not codes. And I'll try to explain that. The only reason I highlight SQLite here is because that is where the codes are held. They're held in a little bit of a SQLite database within Proj. You don't have to understand that. QGIS and Proj and GDAL know how to access that. Let me jump back, sorry. Okay, so quick introduction to WMSs. The previous posting I had, the help will tell you what these addresses are. But in general, when you're adding say from astrogeology WMS, I'll simply go to my data source browser, go to my WMS, and you'll notice that I have a bunch of these available. And if I edit that, I know this is fast, but here's the key. And all these URLs for every single body that we support is listed on our website. And we'll maintain this for as long as I exist. We'll maintain these servers. And I think because they're useful to all our web services, we'll keep them active for a long time. And you'll notice that this is using map server. And we probably a much outdated version. We need to upgrade that. And I would love to add the new codes to the latest version of map server. Essentially, we're saying that, hey, we're grabbing all the layers from Mars that we support. If there's different addresses, you'll need a different URL. When I hit connect, you'll notice that there's a bunch of layers here that we're supporting. HRSC MOLA hillshade blend, there's Themis controlled, and we can ask what style of image we can bring it in. Just you can let it default to PNG or JPEG for the most part. And here's the trick. What I'm talking about in this slide that you'll be able to follow. Well, I guess I should have talked about that. Let me jump forward. So here's our URL. We're actually going to do a new connect to that URL. And then we have a list. We're going to load the Themis control. And this hurts me. We're going to load it as EPSG 4326. That's okay. It just, there's no way to override it in this interface yet, but we will override it right after this. So I'm going to go ahead and add the HRSC MOLA blend, hit add. And again, I'm adding it as Earth. Close, and you can see it right here. So the first thing we do when we add a WMS, I'm going to go to my next slide, is we are actually going to go in and override that definition. And what this essentially is doing is telling QGIS, no, this is what you really are, but it still allows it to connect to the server correctly. And this is just unfortunate. We've been trying to overcome this for a long time. So what happens is when I bring up the properties for this WMS layer, I'll go to the source and I can override it here. So you'll notice in 3.2.2, in Mac OS, it's going to take another probably release or two. I can now type Mars, and you'll notice that there's this Esri sphere, and I must be running the wrong version here. I'll have to load 3.2 to show that this exists. In the latest version, when you type 4990, so 499 is the NAIF number for Mars. So we're using those same coded values. When I type 499, you'll notice that there's about 30 to 40 map projections for Mars. If I type Mercury, which I believe is what, 299, I think, then you'll see about 30 projections for Mercury. And you'll notice that right now in your version, in 3.6, this has been around for many years, probably 10, I don't know, 8 to 10 years. If I type Mars, you'll notice that there's a Mars sphere in here. If I type moon, and it says Esri, and you're like, wow, what is this? What is this Esri code? That is just the reason QGIS started supporting Esri codes, and Esri has been supporting planetary for the last 15 years. And so eventually these Esri codes made it into QGIS. It's a good thing. So until the IU codes come into the system, we always have these backups of Esri. So I'm actually going to take my WMS, I'm going to overwrite it with the Mars sphere. And again, I've loaded it, and now I can overwrite it. I hit apply. And now this surface knows that it's Mars, and it'll do the right thing. So horrible workaround, but I talk about this on my blog, and we'll have it shared in this presentation. So to go back to these codes, if you're in the latest, greatest version of GIS, here's an example. Here's how you use these. It's the IU_2015, such that we can have new dates. This is the NAIF code. The 3 first digits are NAIF. The last 2 are the proposed projections that we support for Mars. And if I type Mars or 499, you'll see about 30 projections. Orthographic, Robinson, sinusoidal, equi. These are not every projection you could ever support, but they are kind of well recognized, well used projections. And you can always grab these definitions, update them, and assign a custom projection from these files. So if anything, you can use these to build your own projections. So again, this is in the latest, greatest. You might not see all these yet. And so WMSs work, but you have to override them in QGIS. In ArcMap, it doesn't care that it's Earth. It will actually jump between Earth to Mars, to Moon, to Mercury for you. So you don't necessarily have to override it. It will do the right thing behind the scenes because it'll do the transformation for you. So that's the workaround. When you talk about nomenclature, you can do the same thing. We support nomenclature from 0 to 360 and also -180 to 180. So there are WMS layers. We also support the nomenclature as WFS. It's a little more temperamental in QGIS because we support it in a 0 to 360 system. QGIS doesn't always like that. So I'm probably going to skip this, but this is basically a really quick tutorial on how to make your own custom projection. So I said we could use those codes. We can grab that definition as a well-known text. We can paste it in here and update the center. So what I've done is I've made my own custom projection for Jezero Crater. Oh, that's my timer. So I'll try to wrap things up. And then there's a nice little validate. You can do it as well-known text or a proj string. When you actually look at those coded values, those coded map projections you can steal from, you can copy either proj or well-known text. So when we talk about well-known text, we're talking about the projection definition here. So I've made my own Jezero map projection, which is centered on the landing site. It's great for being able to make sure that QGIS understands that there's minimal distortion for that region. And it works well. The WMS will project on the fly to this location. Any other COGS will project on the fly to this location. So let's, and you'll notice that when you start setting these, you'll start seeing this IU definition. If I set my projection, I'll go to my QGIS projection. Right now it says unknown. That's not necessarily good. But I want to make sure, and I can select my Jezero local projection because I've added it as a custom following those instructions. And it should jump to custom. It says current. Still says unknown, but if I hover over it, it says Jezero local projection. And pop this over. Okay. So we talked about, and how do we know it's working? This is a great plugin, coordinate capture. I can set any projection I want in this window, and I can double check that it's coming out in meters or in lat long correctly. You can actually capture values if you want to on a text file or a notebook, or you can just stream. You can stream your location, because right now you'll notice the coordinate system is streaming in meters. Using this coordinate capture, I can have this pop up in this window here, and I can stream in lat long. And it's independent of the current map projection because I've set a new projection for it. So great little plugin so that you know that you're working in the right system. I'm going to talk about this for 2 seconds. Within this link, you'll find a bunch of tiles. This is one of those layers. This is a 1 terabyte layer. I'm going to zoom out a little bit. So this is streaming from an Esri Amazon cloud server that they hosted for us. Not only is the CTX Caltech mosaic in here, but there's HRSC and MOLA merge as a DEM. There's the high rise 20 terabyte. Understand it's uncontrolled data. This CTX mosaic is also uncontrolled. So technically we can't call this CTX mosaic foundational. It is good, it is nice looking, but we can't call it foundational because it's uncontrolled. But sometimes we have to live with uncontrolled data. So this is a example of a Amazon hosted tiled WMS serving terabytes of data. And so for QGIS, I explained that you have to download the zip file and and then you simply drag in these configuration files into QGIS. And what are these? They're simple TMS, tiled map definition, and it says what the address is. So we're going straight to Esri servers, and we're bringing in a tiled map service. And you'll notice this is amazing that we're actually using very verbose definition of Mars instead of codes. That's great. I wish that all services had that, but we're still stuck with these codes. 2 more slides. So now let's talk about COGS. Let me see if I can go to this. Sorry, my Amazon device is talking to me. Stack browser. Oh, hush up, Amazon. I'm going to go to Mars. This is a stack, very beta. This is a stack collection. They are MRO CTX ASP generated DMs. I go here, I find it. There's an API to do spatial search, to do temporal search. We're releasing all the documentation on that. There's ways to download these on the command line, or you can grab these. This is a COG. This is the area. I look at the assets, and there is a DM, a hillshade, and ortho. All these are stack assets that are formatted in a COG. This address, I can go right to here, copy the link, take my COG, and I can go to my browser, and I add a raster through HTML, paste that link, and I hit add. Now, what this is doing is this is using QGIS is using GDAL behind the scenes to add the COG from the Amazon hosted website. I now have it loaded. I can zoom to layer. And if I set the stretch, this is real data. It's not JPEGs. This is real data. I can do my stats. Let me do cumulative. And there's my image. Again, these are ASP generated, so there's lots of holes in the DEMs. But this is an ortho. You'll notice it's in 32-bit. So again, we're streaming a 32-bit image straight from an Amazon bucket, and I didn't have to download it. Now, how many can QGIS handle? Probably not hundreds. Then you can start getting into things where you download and do virtual mosaics, or you can actually do virtual mosaics of COGS. Pretty amazing. I'll show another example. This is another COG. I'll zoom to the layer, turn it on. This is actually a DEM, 32-bit DEM, streamed straight from Amazon. And I can say, hey, I want to make a hillshade of that. And there's my hillshade. I can do profiles. It's just like a local file. So the bottom line is that while we're still dependent on WMS, we're still dependent on tiled map servers. For data and potentially mosaics, we're really looking into understanding how stack and COGS can emulate a very easy mechanism for anybody to support streaming services. You'll notice that for whatever reason, on some versions of QGIS, there's this option for hosted TIFFs called number of threads. If you can up that, it'll make these services even faster. On my version, I've never seen this installed. This is a GDAL trick. You could probably set a GDAL environment. The number of threads you have on your PC will help this service. It'll actually grab the tiles even faster from the Amazon cloud. So this is the loaded cog. And that's basically it. I wanted to leave some time for some questions, or I could simply fill up the time with more demos. Looks like we might have some. I will make this presentation available. I'll ask the coordinators where to put it, but feel free to use our COG resources. It might come up and down. We had trouble last week with the Kaguya data set. It looks like it. Nope. Yep. So you're going to find that this site's kind of going up and down. The actual data hosted should be stable, but this browser might be going up and down with different metadata as we get ready. So the only 3 catalogs we're currently supporting are Moon, Mars, and Jupiter. And we're starting to add more and more. We're working on Themis, individual images, and so this doesn't it's not trying to compete with the Trex or the JMARS or the quick maps of the world. It's trying to become more data friendly and data siloed friendly. What do I mean by that? We're not trying to host an application for you. We're trying to host the data that can be used in multiple applications. And again, if you can't use this, if you need it in MATLAB and it doesn't know how to do COGS, simply download it. It's a GeoTIFF. Okay, I will shut up. Thank you for your time.
Thank you, Trent. Thank you very much. That was super interesting. Actually, I guess Angelo prepared, or maybe Giacomo prepared some COG to be used during the exercise next days. Right, Angelo? I don't know.
Yeah, for the Mars.
Yeah, for Mars, we saw we were able to actually compress the data very well.
And the best thing about COG is it basically the GDAL application, GDAL Translate, does it for you. There's no thinking. It'll just do it for you.